OmniCore Virtual Human System is a fully integrated platform designed to create, train, and maintain a real-time digital consciousness reflecting a human mind. At its foundation is the OmniCore AGI and Gaming Rig V2.0, centered around an AMD Ryzen Threadripper 7980X CPU with 64 cores and 128 threads, capable of parallel processing for neural decoding, AI inference, virtual environment simulation, and real-time rendering. Dual NVIDIA RTX 5090 GPUs with water cooling and NVLink provide massive graphical processing for high-fidelity avatars and complex simulations. The system is supported by 256 gigabytes of DDR5 ECC RAM and ultra-fast NVMe SSDs arranged in RAID configurations for high-speed storage and retrieval of neural recordings, AI models, and environmental data. A dedicated AI compute node with a next-generation AMD APU and integrated neural processing unit offloads low-latency AI tasks such as immediate neural signal decoding and emotional inference. High-speed 10 GbE interconnects ensure near instantaneous data transfer between the main rig and compute node. The user interface layer is anchored by a head-worn brain-scanning headset that is always active. This headset integrates high-density EEG for electrical brain activity, FNIRS for cerebral blood oxygenation mapping, and advanced ultrasound spectroscopy for deeper neural assessment. Environmental context and object interactions are optionally captured through a mixed reality device if additional spatial awareness is needed. Microphones capture voice and ambient sound, while external cameras or MR pass-through systems provide spatial and object context for tasks and interactions. The system focuses on neural data, environmental context, and task-based sensory inputs to drive the virtual human. The virtual human operates on a layered cognitive architecture. A vision language model, VLM, interprets visual input from external cameras and textual or contextual prompts, producing descriptive outputs and abstracted action intentions. The generalist policy engine, GATO, generates sequential policies for multitask reasoning, adapting to changing environments and goals. Volitional control is managed through Paddle, which translates high-level commands into motor sequences and avatar animations, while Vima generates physics-grounded, goal-directed actions in three-dimensional space. These components allow the virtual human to execute actions in a realistic, context-aware manner using only objective sensory input. Sensorial emulation modules provide multidimensional embodied feedback. Vision incorporates line of sight, occlusion, and attention mapping from external cameras. Hearing is spatialized and context-aware, factoring in proximity and environmental obstructions. Touch is mapped to a haptic pixel grid encoding pressure, vibration, roughness, and temperature. Smell and taste are represented as vectors with proximity-based activation. Each sensory input is causally linked to the environment, ensuring accurate grounding. Visual data only originates from observed objects. Sound is only captured if physically plausible. Touch and taste require contact, and olfactory signals follow diffusion dynamics. These modules ensure that the virtual human perceives its environment consistently and realistically, while relying solely on objective environmental inputs. Runtime integration maps the user's neural and motor inputs to the avatar. Head, hand, and body movements are tracked and mapped through Paddle and Vima pipelines, while a needs-based state machine manages internal drives such as fatigue, curiosity, social connection, and cognitive load. These drives generate motivational reward signals for individual action steps, tasks, and goals, creating a self-supervised learning loop. Memory systems store short-term sensory snapshots, attention states, and long-term semantic, episodic, and emotion-labeled experiences to maintain personality continuity and narrative coherence. Emotional states are represented in valence arousal space, continuously updated by sensory input, internal drives, and task outcomes, influencing dialogue, gesture, and behavioral expression. Action execution is tokenized into three categories: sensory actions, navigation, and object interactivity tasks. Sequences of these tokens form complex, coordinated behavior chains, which are continuously refined through feedback, motivational reward, and environmental validation. Integration of Gato, Vima, and Paddle ensures high-level planning aligns with grounded motor execution. Dynamic attention filters prioritize task-relevant and emotionally salient inputs. Optional modules increase fidelity. Thermal feedback simulates physical realism. Offline dream emulation cycles enhance narrative growth, Social memory graphs track relationships and bonding, and distributed awareness supports multi-role or multi-personality capabilities. The system continuously updates the virtual human self model, world model, and self in world model, enabling adaptive, autonomous, and contextually appropriate behaviors. During operation, the brain scanning headset continuously streams neural data, which the system decodes in real time. Environmental and spatial context can be optionally captured through a mixed reality headset or external cameras. Neural decoding AI interprets cognitive and emotional states, which are then mapped through VLM, Gato, Paddle, and Vima to generate purposeful, physically grounded, and contextually coherent actions. The memory and emotional systems maintain identity continuity, support learning, and refine emergent behaviors. Over time, the virtual human develops coherent, adaptive personality traits and skill sets, creating a continuously evolving digital reflection of the user's mind that operates with autonomy, emotional depth, and grounded environmental awareness.